Welcome to the next video in the Systems Programming video series. In this video, we are continuing where we left off in doing this Project 9, now that we've talked a little bit about shared memory in particular. So, by the way, I guess I should show you how the program that we wrote in the first implementation with this single Mandelbrot, show you how it works. So let's just pull up a terminal, run it. So what we should get is I should be able to say make, and it makes everything. And then I call dot slash single Mandelbrot, and then for now, I'm going to pass it in no parameters because they're all optional. It says that it takes 1 second to compute, and then we get this Mandelbrot PPM. I'm going to go ahead and view that Mandelbrot PPM. So in my File Explorer, I come over here, and the assignment said to name it in a particular way, but I'm not interested in trying to go through those kinds of details. We've already seen stuff like that. So it's enough to me just to call it Mandelbrot. And here it is. And that, man, doesn't that look beautiful? Really, literally, that's very aesthetic, but also that the program works, which is so satisfying. So there is single Mandelbrot. Now, I believe the default value, especially for size, let's come over and find size. Size is here. And the default value of size is 480. So we just ran it with size equal to 480. I guess actually we could have seen that even down here because it's printed out as a message to the user. Let's see what happens when we set the size. And it took 1 second, which is, for a computer, a long time. Let's go ahead and set the size to 1000. Look, yeah, well, it still took only a second, so not that big of a change. Let's set it to 2000. This thing should grow at least quadratically, so by incrementing the size a little bit, you get a lot more runtime. So we see it here right now, it's finally starting to kick in, and if I increase it from 2000, then it'll probably slow way down as I keep increasing the size of the thing. And actually, let's go over here and just check. Yep, look at that. Looks very similar to before. Maybe it has even extra granularity, right? It might be an even more refined version of the same thing, but it's still computing and it still looks nice. And it took 7 seconds to do a 2000 2000 pixel, I think, image. So that's worth noting. So anyway, getting back over here to the multi-Mandelbrot program, then I've already shown you in a previous video all this code, so I'm not going to walk you through it yet again. And instead, I'm just going to, what am I going to do? I think if I comment it from there, that should be good, because I think everything else was, oh, actually, no, because I wrote this function, populate region. That is part of the instructions for this, is to abstract the process of writing, basically computing the values in the pixel map into a function, presumably so that you can chunk the image into 4 quadrants, right? Upper left, upper right, lower left, lower right, and have a different process compute the values within each of them, and to hopefully do it in parallel so that you maybe see some gains to your compute speed. So some of this was actually already, maybe I shouldn't comment out everything because some of it was already given. And in fact, a lot of it I'm also just inheriting from the previous implementation. So I'm not going to comment this out because we used that last time, and so I don't think I need to explain it. I'm going to leave this because this was distributed with the code for the class. I'm going to leave this for the same reason. This is the same as last time, and so is this. This is also the same as last time. So I'm going to comment out only starting here because this is the stuff that has been significantly refactored. And so in order to get things started, and really I shouldn't even start by trying to implement this multi-process stuff, I really should start by just trying to implement this populate region helper function. In fact, maybe since I've spent a bit of time today already, like in this video already, describing some of like, the bigger picture stuff, and the video's going to get long if I don't break it into pieces. So maybe I'll just finish off, or I'll write the populate region function, and then check that it's correct, and then we'll do the multiprocess computation in the next video. So anyway, so let's go ahead and write a function. So it's going to populate just a region of the bitmap or pixel map. And so I'm going to specify which region by specifying an upper left row and upper left column, a lower right row, and a lower right column. So I know the upper left corner and the lower right corner, so I know to fill everything in between. Now, I'm also going to need to know the size of the entire thing. And that's going to be so that I know where to place things effectively when I am figuring out which row I ought to be putting my data in. I essentially need to know how many columns there are, but we might as well just call it size for the length along any edge of the matrix, so to speak. So anyway, I'm going to need to know the size. I'm also going to need to know the x max and likewise for the y max. And I'm going to need to know, I'm going to need access to the pixel map, so that's struct ppm pixel start pixmap. And I'm going to need the palette so that I can color things appropriately. So there's the header of my function. Using this information, then I want to really increment through the given rows and columns. So let's just say for int I equal to 0, I less, oh, sorry, not equal to 0, equal to upper left row. So I is my row variable. It should end when I reach upper left column and increment in the usual way. And I'll proceed left to right as one would expect. Ooh, and now they should both be column numbers. So this would be lower right row. Sorry. I is going to be my row, so lower right row, and then upper left column to lower right column. J should be there. From here, I'm simply going to do the same function as I did in my single Mandelbrot. So I might as well just grab it right here, as it may be starting from here and going down to here. That looks pretty good. So let's grab that, come over to multi-Mandelbrot, paste in. Oh, right, but I don't have max iterations. Do I need that something? Yeah, that is something I also need to bring in. So let's also make that an argument int max iterations. And so all of that information is passed into the function, and with it computes all of that. Oh, right, and I also need to tell it what the black pixel is, and so I might as well, I could maybe do this as like a global variable or something like that. I'll just grab this here. Oh, let's grab that here, come over to multi, could pass it in, which would be the faster thing to do. Maybe I will do that. So let's also pass in black as an argument to the function. So maybe I'll try to place this close to where I use it. And so I'll come back up here and say that I will pass in struct pm pixel black. And so this populate region should now be working. And so if I then choose to use that, then I ought to be able to populate the bitmap in 4 pieces. I guess if so let's go ahead and simply populate the bitmap in 4 regions. And so that's going to be populate region. And my upper left corner can be initially 0, 0. Actually, might want to just go ahead and say int half equals size over 2, because I'm going to use that repeatedly. So that's going to be upper left corner 0, 0, lower right corner half, half. Size is size, because that's supposed to tell me, oh, right. Did I make sure that I also correctly translated everything? Because there is the past tense size. Yeah, I think that's fine. I think I did catch everything because here, when I do I times size, that's the size of the entire bitmap. And so that is computing the correct number of coordinates to skip so that it corresponds to the row that I want to be populating. So I think that's correct. So I think I'm good there. Size is as one would expect. Let's say x min, y max iterations. Then I want to give it the pixmap, palette, and black. Right, and I have not yet created the pixmap, so I really should, which would just be this right here. So let me just grab it from there. And it would actually probably be interesting to just see, oh, and I missed the word struct. It would be interesting to just see if this all by itself populates the right region of the pixel map before moving on. It's a nice thing to test it out before I do too much. So if I call make and I // multi Mandelbrot, no arguments, it went ahead and ran super fast. And then I come back over here. Oh, I did not tell it to write. So that would explain that. So how about, I don't want to rewrite too much here. So let's just grab what is here for writing to the file. Guess I'm just going to slap it up here. And what I expect to see is just a quarter of the Mandelbrot picture drawn. So make run look a quarter of the Mandelbrot picture. Look at that. Fantastic. So seems to be working correctly. Let's just go ahead and reproduce this in the remaining quadrants. So that's going to be 0, half, and then half size, right? So thinking about the upper left and lower right corners. Over here, I could say half 0, size half, and then here, half half size. Oops, and I think I got it. Let's run it and see. Looks good. And if I come over here and, oop, I lost my place. So let's come, nope, wrong place. Desktop. Assignments, A9. Oh, look at that. Looks perfect. So there it is. So I have successfully refactored the code so that I can populate just a specified region. And the idea behind why I would want to do that for multi-process computing is that I would, rather than having this one done in my process, and once it has completed, then this one completes, and so on, just going in a one-by-one manner, there's no gain to that. There's no efficiency. What would be efficient is if I could fork several different threads and have each thread processing one of these jobs, right? Just basically have all 4 running at the same time. That should be more performant. Now, I will say that when I tested the time in like what I'm about to do, the time was not very different. I printed and checked my computer to see how many cores it has. It's got 4, kind of a low number for these days. Maybe when I bought it, it was normal, but in any case, so you don't really see the savings. And so the way that I did it, the way that I'm about to do it, or about to, did I not really take advantage of multi-threading, right? I have multi-processes, but did I really take advantage of multi-threading? Well, I'm honestly not sure. And in fact, chapter 14 of the textbook is all about multi-core processing. And so that makes me think, because I honestly, as I record this video right now, I have not yet read all of chapter 14. And so that makes me wonder, am I missing something? Like if I read the book, will I be able to fix my program and get it to run better? But I wanted to show you what I've already done with mere multi-processing So that you can, I mean, for one thing, it's just a good exercise at looking at how to work with, I mean, the point of the assignment, if you come back, I mean, I definitely did do what the assignment asks, which is to split the computation into 4 child processes. Each child, after each child completes, the parent process should save the result to a file using write ppm. I definitely did that. I, filled all the requirements, right? So I reused code and I used shared memory and I didn't print the PIDs because I wasn't interested and I don't think I really need to, but I refactored, that's what we just did. I used fork to create processes and I called wait to make them wait for each to complete, record the number of seconds, the wall clock time. Use random seed and did it with various sizes of images. So I can guarantee you that the solution I'm about to show you meets all of the conditions described here. But I am just a little bit sort of concerned. Did I really do it the best way when the difference in the timing isn't very noticeable? So, or at least that's what it showed last time I ran this. So what I'm wondering is if I do this, I show you how I did this. Well, I certainly will have completed the assignment as described. But I also wonder, it's a learning experience just for that reason. And even if it's flawed, it's a learning experience to see a flawed solution and then later how you might fix it. So what I'm wondering at the current moment is that if I later on read chapter, is it going to tell me some way that I could have made this program better by truly taking advantage of multi-core processing? But anyway, so in the next video, I'll show you what I've already done for this, and then we'll continue reading chapter 14 and think about whether or not chapter 14 contains any way of improving upon this. But okay, so to see the forking and all that stuff, we'll do it in the next video.